Alright, welcome back, and this is where things get a little bit trickier. At least in my experience, this is some of the areas that are a little bit harder for students to grapple with. So I'm going to take my time and get through this a little bit slower than when I was going through the binocular depth cues. And again, I try to base these things off the book, so if you're following along at home, don't rely just on these videos. If there's anything that is specifically kind of stands out to you is a little bit confusing, go back and check out what the book has to say. I try to use the same visual examples for that reason. Alright, let's talk about binocular vision. So in other words, two eyes, how they perceive things. So whenever we are looking with both eyes, we can engage in something called accommodation. And so you may remember we talked about accommodation in chapter 2, and I was talking about with the lens and how the lens can be, let's see, if you were to use, I don't have a good example. If you were to have, actually, here we go. So if you have this surface, look, this is almost kind of like a lens. Just imagine this is see-through. That most of the time lens, whenever you're looking straight ahead, is like this. But we can, if we want to, bend it a little bit like this. Or we can relax it and let it be straight ahead like that. So just again, you can have these muscles, the ciliary muscles, that keep it kind of straight, or that can kind of bend it a little bit. Our lens is basically going to be able to perceive things at different distances. It's going to focus on things at different distances, depending on how much is being bent. So we can change our depth of field using accommodation. So that, what I was just showing you, is accommodation. How can you test this out? Maybe you're just kind of like looking at the slide and you're not really paying attention and it kind of goes blurry a little bit. A little bit of that can be accommodation, where whenever you are looking at the letters, it seems to snap into focus. That is your lens kind of being kind of compressed and retracted from your ciliary muscles in your eye. Okay, great. Now let's look at a couple of other examples. We have convergence and we have divergence. And convergence and divergence have to do with the placement of your eyes, specifically where those eyes are pointing. So if we want to focus on something close to us, we are going to use what's called convergence. So if you were to take your finger and you were to look right at it, where you're crossing your eyes, you're looking at your fingertip right here in front of your face, that is convergence. Whenever we do that, we are converging our eyes to point towards one another to try to get a good focus on something that is close to us. But let's say that we are out in the middle of a field and we think that we see our friend's truck way out in the field. What would we do? Our eyes would try to look straight ahead, right? They would try to turn outward as much as possible to look at something that's really, really far away from us. So when we're focusing on farther objects, our eyes are going to diverge a little bit. They're going to try to move as far away as possible. Alright, so that's just some of the basics. Now let's look at this example. This example you can find in your book. And if you want to, if you have some crayons, you can try it out at home. Basically, imagine that you have some of these crayons set up. You have them standing on top of one another, and so you can tell, based on where they are standing, which ones are closest to us, right? So if we are focused on the red one right here, if you're looking at the red one, what happens is that your eyes are going to turn towards that red crayon. If you're looking at the blue crayon, then your eyes are going to turn towards that. And depending on how inward they are turned, that can tell us about how close that object is. So that if we're focusing over here at the purple crayon, our eyes are not going to be turned in all that much towards one another. They're going to be kind of almost parallel to one another to see that distant purple crayon. So if we're, okay, so that's convergence and divergence. Now we're going to be talking about what's called binocular disparity. And binocular disparity is what I was talking about in the first video when we are simulating 3 dimensions in our entertainment, like in TV and in movies. Okay, so how this works, you may remember I was talking about how one eye gets one image, the other eye gets a different image. So, the reason why this happens is because our eyes are about 2.5 inches apart from one another. So if we're looking at these crayons right here, think about what your left eye is seeing and think about what your right eye is seeing. They're not seeing the exact same thing. So your left eye might see something kind of like this. So your left eye is focused right here on this red crayon. You got the purple, you got the blue, you got the brown. Perfect. Your right eye is going to see the exact same things, but the proportions and the distances are different. So we're seeing basically the exact same information, it's just kind of in a different spatial orientation. And so what that means to us is how far away things are. So, for example, this red crayon, it stays in the center of our vision, but where are the biggest differences? The purple crayon, right? The purple is the one that seems to move the most. And because the purple has the biggest disparity from these two eyes, from the left image and the right image, our brain perceives that as it being farthest away. So, things, to put it a different way, when we compare these two visual fields, your left retinal image and right retinal image, objects that are more different when you compare them are farther away from us. Things that don't change are closer to us. And so, for example, the blue crayon stays pretty much in the same spot, right? And if we go back, we can see that, yeah, the blue crayon is pretty close to us, right? It's just that this purple crayon, which you can't see because of my big dumb head, is in the way. All right, so that's binocular disparity. Binocular disparity tells us how close and how far away things are based on how different those retinal images are. And this is part of the reason why people talk about how whenever you only have access to one eye, if you're wearing an eye patch, that you have poor depth perception. You can still perceive depth. Let's not make a mistake about that. But where things are different is that we no longer have a second image to compare with. That second image that we're comparing things with is going to tell us about how far away things are. Okay, so now let's get into some definitions. And, typically I don't like to spend a whole lot of time on definitions, but it's important in this case. And the reason why it's important in this case is because this is very, very tricky. So if you need to, again, refer back to the book, rewind this video, things like that. So, binocular depth cues. The first thing that we're going to be looking at is the horopter. The horopter is basically going to be where our two eyes are going to converge. In other words, this is the point of zero disparity. So, if we are looking back at this, the horopter is going to be this red crayon. Why? Because the center of our left eye is looking at it, and the center of our right eye is looking at it. That is the point of zero disparity. So, that's the horopter. So again, if you're looking at it like this, the horopter is going to be, because these two eyes are looking right here, that is going to be the horopter. Okay, great. So that's the horopter. The second part of this is going to be the Vieth-Muller circle. The Vieth-Muller circle is very similar to the horopter, except that it's a circle. But what is important about it is basically that it is an imagined circle on which the horopter lies. So imagine, that you're looking right here at this red crayon. You're going to have an imaginary circle that kind of moves around your field of view. And anything that is on that particular circle is going to appear to be one image. It is going to appear to not be blurry. You'll be able to focus on it very easily. I'm going to revisit this in just a second, because the next part will kind of clear some of this up. And that's the Panem's fusional area. The Panem's fusional area is going to be the spot a little bit in front of and a little bit behind of the horopter that is going to make things crystal clear to us. Okay, so now let's take a step back. Imagine that you are looking at, maybe if you can do this with your finger if you want to, you can do it with a pen if you want to. So take the pen, hold it a little bit away from you. So if you're holding it a little bit away from you, trying to get it so you can see what I'm doing. If you're looking at it, I'm looking at it, you got your eyes on it. Now think about what's direct. Don't look at it though. So keep looking at the pen. The things that are behind the pen, how do they look? Right now I'm looking at there's a picture frame back there, but it's totally blurry. It is very, very blurry. So even though my eyes are kind of pointed at this pen, things that are beyond the pen are blurry. Okay, so If I were to take this pen and I were to put my finger very close to the pen, a little bit behind it, I can see both the pen and the finger in perfect clarity. It's perfectly fine. I can put my finger a little bit in front of the pen, and while I'm staring at the pen, my finger is perfectly fine. That's because my finger in those instances are falling within the Panem's fusional area. They are falling within an area that our brain is basically going to combine these things, going to put it together, make it crystal clear. This is the center of our visual field. This is something that is important to us, and so we are going to process it using as much visual processing as we can. It's not in our periphery. This is something that's important. So the Panem's fusional area is going to take anything a little bit in front of or a little bit behind of that horopter, in this case it was the pen, and turn it into something that is easy for us to see. Now, if I'm looking at the pen again, I already told you that that frame behind it is very, very blurry. That's because it falls beyond the Panem's fusional area. But if I were to move my finger pretty close to my face, and I'm still looking at the pen, now my finger is really blurry. And that's because it falls outside of Panem's fusional area. And so Panem's fusional area is this really specific area where our two eyes are going to, or actually maybe I should think of, Panem's fusional area is what happens in the brain. It's where these two images are going to appear as one solid image. That's part of the reason why whenever things fall outside of Panem's fusional area, they appear to be double vision. Whenever the finger is really close to me, it looks to be double vision. Whenever things are farther away from where I'm looking, it appears to be double vision as well, because they are actually two separate visual fields. One that is from a right eye, one that is from your left eye. So let's go back to the Vieth-Muller circle. The Vieth-Muller circle is this, like I said, it's this imagined kind of circle that's unique because if I'm sitting here staring at this pen once more, that there is basically an imaginary circle moving around this in which things are going to be pretty much, whoops, you can't see what I'm doing, pretty much diplopic, or that they are going to be clear to us, that they are going to be fused together, those retinal images. But if you get a little bit in front of the Vieth-Muller circle or a little bit behind the Vieth-Muller circle, then things become double vision again. Alright, so those are some definitions. Diplopia is whenever you have double vision, basically means that things are closer or farther away from where our horopter is. Okay, if you cross your eyes, everything looks diplopic because your horopter is going to be right here in front of your face, and so everything appears to be double vision because you basically have these two retinal images that your brain is saying, that doesn't matter. What really matters is what you're focusing on, which is right here in front of your eyes. Okay, so the last little bit of this video, I want to talk a little bit about cross disparity, and I've already talked a little bit about this stuff a little bit, that cross disparity is whenever we are going to be looking at things in front of the horopter. So, for example, if I am focusing on the pen here, and something is in front of that pen, it is going to appear to us to be two separate images because of cross disparity. So it's falling outside of Panem's fusional area, and so it appears to be diplopic, and it appears to have double vision. That is cross disparity. If we do the opposite, if we're looking at something really close to our face, everything behind it appears to be crossed as well. It appears to be double. That's uncrossed disparity. So cross disparity, both of these are bad, right? Both of these are going to be blurry to us. And you can kind of even look at the retinal images here to see kind of how they change depending on what it is that we are focusing on. Cross disparity, things are going to be blurry because they're too close, or they're too close to us from our horopter. Uncrossed disparity is they're going to be too blurry because they are beyond our horopter. Finally, free fusion is going to be whenever you allow your eyes to basically kind of wander and move beyond an image so that you can kind of see something. And you may have seen these magic eye posters. So these were all the rage in the 90s. So when I was in 4th grade, I remember, so I don't remember what year that would be, but it was sometime in the 90s. When I was in the 4th grade, people were crazy about these posters. You'd find them in almost every elementary school classroom. These posters that look exactly like this, and if you're like me, you're looking at this and you're like, I have no idea what this is supposed to be, right? But you can find a hidden image in it if you cross and uncross your eyes. Usually what people will say is that the best way to do this is to look beyond the image. So, for example, this works best usually, I find, if you have like a tablet or a phone that you're watching this video on, or this PowerPoint on. If you're looking at this image and you have the PowerPoint close to your face, and then you imagine that you're looking behind it, that you're looking at something next door, then sometimes something will kind of stick out at you. I don't remember what these images are supposed to be. I've never actually gotten these things to work super well for me, but I have shown them in the classroom, and people have told me what they are. I just can't remember what they are. I think there's a word in this one, and there's like a specific animal in this one. This one is not a bad word, though, so it's not like the F word or whatever. All right, so I'm going to pick up on this next little bit in the next video because it's going to get a little bit, we're not completely out of the woods yet. It's still going to be a little bit kind of crazy complicated here, and so I want to take another video to elaborate on how 3D movies work, and then talk a little bit about the development of the eye and why that's important. All right, I'll see you later.